Welcome. Let us continue the discussion of the effects of the RF pulses. How does the density operator transform in the presence of RF? Because we need to know all of such things. How does the density operator transform under the influence of different kinds of Hamiltonians? So, the RF constitutes also one Hamiltonian, and we actually saw last time how to calculate the evolution of the density operator in the presence of the RF. So, we had this solution here. We started off with the Liouville equation and we represented the solution like this: rho of t is equal to e to the minus I by h cross h naught t, rho star t e to the I by h cross h naught t. H naught was the main Hamiltonian, and H1 there was the RF Hamiltonian was represented by H1, and this represented the interaction representation. And we also show after detailed calculation that under the resonance condition we have the rho of t is equal to the e to the minus I by h cross h1 t, this Hamiltonian t, rho of 0 e to the I by h cross h1 t, and this h1 represents the Hamiltonian of the RF. And we also demonstrated that e to the minus I by h cross h1 t essentially represents a kind of a rotation operator e to the minus I beta iq. We will explicitly demonstrate that further, how this will represent a rotation. Okay. And therefore, having said this, we will say rho of t is equal to e to the minus I beta iq, rho of 0 e to the I beta iq. Notice here q can be x, y or z. Generally z is only for rotation around the z axis, therefore it is not kind of an effect of the RF pulse, but general rotation along the z axis can be represented in the same manner if the rotation is about a particular angle beta. And we define now this as the rotation operator, call it as rq beta is equal to e to the minus I beta iq, and q can be x, y or z. So therefore my rho is now rq beta rho of 0 rq minus 1 beta. Okay. And that is the same equation here. We now calculate explicitly the effect of the pulse on the density operator. So to begin with, let us take the equilibrium density operator Iz. Okay, rho of 0 Iz. Of course, the rho of 0 has this other entities, but the operator part is the Iz only. Therefore, we will pick up only the Iz part of the density operator, equilibrium density operator, and put that here. So the rho of t for rho of 0 I put here Iz, rq beta Iz, rq minus 1 beta. So in order to do this, I need to get the matrix representations of these operators, right. These were in the form of exponential operator, whereas Iz I knew is in the matrix operator. Therefore, I have to put this also in the form of a matrices. So for this we will calculate the matrix representation of the RF pulses. We have to get explicit matrix representations for these terms. So how do we do it? So let us write here again rq beta e to the minus I beta iq, q can be x, y or z. Now we have earlier seen matrix representations of the operators Ix, Iy and Iz, okay, and these ones we have calculated matrix representations of the operators Ix, Iy and Iz, and those ones were simply are given in this except for the factor half. So therefore this can be represented as half sigma q, where sigmas are the Pauli spin matrices. Basically Iz is half into 1 0 0 minus 1, Ix is half into 1 0 1 1 0, Iy is 0 minus I 0. Now we take away the half, you have this matrices 1 0 0 minus 1, and this is represented as sigma z, and likewise sigma x is given as 0 1 1 0, sigma y is given as 0 minus I 0. These are called as spin matrices. For a single spin half, these are called as Pauli spin matrices. You can easily verify that the Pauli matrices satisfy this condition. Sigma z square is equal to sigma y square is equal to sigma x square is equal to 1. But one notice here, this 1 is a unit matrix. It is not just number 1. This is unit matrix 1 0 0 1. Okay. So this will be useful for us to calculate the matrix representations of the individual operators. So here I expand this exponential function as a series. This is a typical expansion of the exponential function e to the minus I beta ix. I write it as e to the minus I beta by 2 sigma x. So ix is half sigma x, and you write it as a series 1 minus I beta 2 sigma x. Notice here there is a unit matrix here, this is unit matrix here. Then you have the sigma x matrix, and here what we will have? Sigma x square, I by 2 whole square and sigma x square, and sigma x square is a unit matrix because we have seen that earlier, right? And this is minus 1 by 3 factorial I beta by 2 to the power 3, and this will be sigma x cube. But sigma x cube is sigma x square into sigma x, and sigma x square is unity. Although the explicit unit matrix is not written here, but it is there, remember this, okay. And likewise 1 by 4 factorial I beta by 2 to the power 4, and this is sigma x is 4, sigma s 4 is again 1. Therefore, you will get this infinite series. There are terms which depend on sigma x, and there are terms which do not depend on sigma x. Now we regroup these terms and we say put all these terms which do not depend upon sigma x as 1 minus 1 by 2 factorial beta by 2 to the power 2. Notice the unit matrix is present here, and 1 by 4 factorial beta by 2 to the power 4, again unit matrix is present here, and likewise, and this bracket closes here, and the other terms are minus I beta by 2 minus 1 by 3 factorial beta by 2 to the power 3, and all of these then have multiplication with sigma x. So therefore this will be, what is this? This first bracket. This first bracket is actually an expansion of the cosine beta by 2. This is the series expansion of the term of the function cosine beta by 2, and the terms in the second bracket are represent the series expansion of the function sine beta by 2. Therefore I have here cosine beta by 2 multiplied by the unit matrix, and this is, we can write this unit matrix here, okay. So and the I am minus I sigma x sine beta by 2. So what does this give me? Put this in the matrices, matrix form explicitly, cosine beta by 2 1 0 0 1 minus I sine beta by 2, and I had the sigma x is 0 1 1 0. Therefore now if I put beta is equal to pi by 2, see if I put beta is equal to pi by 2, then what do I get? I get cosine 45 here and sine 45 here, and both of them are equal to 1 by root 2. Okay, so therefore e to the I minus e to the minus I pi by 2 ix gives me 1 by root 2, and if you add these here, 1 gives me 1 minus I 1, right. So this is 1, and this gives me minus I, this gives me minus I, this gives me 1, and 1 by root 2 factor comes out here. So similarly for Ry pi by 2, this is the pi by 2 pulse applied along the x axis, RF is applied along the x axis. This is again now a pi by 2 pulse applied along the y axis. So this gives me 1 by root 2 1 minus 1 1 1. Okay. So similarly you can calculate matrices for the pi pulses. If I to choose beta is equal to pi, then Rx pi is e to the minus I pi ix, and this gives me 0 minus I 0, and Ry pi gives me e to the minus I pi iy, this gives me 0 minus 1 1 0. The effect of these pulses on the density operator can be explicitly calculated using these matrix representations. So for example, for a density operator represented by Iz, so this is the easiest example to take. So we take the equilibrium density operator represented by Iz, and we will calculate what is the effect of Rx pi by 2. Is it actually a rotation? Now we will actually demonstrate that this pulse does make a rotation. Okay, how do we show that? So the density operator here, rho of t, this is the same equation back here, Rq beta Iz Rq minus 1 beta, and therefore I put here Rx pi by 2 Iz and Rx minus 1 pi by 2. So now we calculated what is Rx pi by 2, that was this, and now I get here a 1 by root 2 from here, 1 by root 2 from here, and this gives me 1 by 2 in the matrix. Therefore I have a 1 by 4, and this gives me 1 minus I 1, and Iz is 1 0 0 minus 1, half factor is already taken away here, and the inverse of this Rx ka inverse of this matrix is this 1 I 1. How do I say this? Because now you see, if you multiply this matrix with this matrix, you will get 1, right. So this product you take 1 1 here, okay, and this gives me 1, and minus I square. So minus I square is 1. So therefore 1 plus 1 gives me 2. We can actually do that. Let me do here the 1 minus I 1 and multiply by 1 I 1. So this gives me, this is equal to 1 minus I square, this is 2, and this is I minus I, this is 0, and minus I plus I, this is 0, this is minus I square is 1 plus 1, this gives me 2, and therefore if I take this 1 by root 2 1 by root 2, I will have 1 by 2 here, therefore this is equal to 1 0 0 1, right. So therefore what I have got, therefore this is the inverse, this is demonstrated that this matrix is the inverse of this matrix. So now if I multiply all these 3, what do I get? I get half 0 I minus I 0, and this is minus Iy, okay. So what I have got? As a result of this, Iz has become minus Iy. Therefore there is a rotation, 90 degrees rotation, right. Now therefore we have explicitly demonstrated that the Z magnetization is rotated onto the. So if I had the Z magnetization here, and if I applied the x, this is the xyz coordinate, the axis, and this rotates the transverse magnetization along this. So I get here magnetization rotation to minus Iy. So clearly the Z magnetization is rotated onto the negative y axis. Okay. Now for 2 spin system, that was simple for 1 spin system. For 2 spin system, of course it is also simple, but we have to do a little bit more calculation here. Now there are 2 spins, both are independent, right. Now I want to calculate the matrix representation of the pulse for 2 spins. So both are I is equal to half, so they have this one spin here and the second spin here. So let me call them as spins k and l. So if I call this as spin k and this spin as l, right, and each one of them is independent. Therefore if I want to represent a matrix which represents both of them, I have to, when I take the product means I can't take a simple matrix multiplication here, I have to take what is called as the direct product. So direct product means each of these element, when I take the multiplication of the direct product means if I take this and multiply I put the entire matrix here, multiply the entire matrix with this element, therefore I get here 1 minus I 1. Now so far as this element is concerned, I multiply minus I with this entire matrix, therefore I get a minus I here, and minus I into minus I, this gives me plus I square, that is minus 1 here, and likewise minus I into minus I gives me minus 1 here, and minus I into 1, that gives me minus I here. So similarly I get here minus I minus 1 minus 1 minus I, and for this I get 1 minus I 1. So now you see this is a 4 by 4 matrix. So I should get a 4 by 4 matrix, right, that the Ix operator for a 2 spin system is a 4 by 4 matrix. So we get that by doing this direct product of the individual spins, because the 2 spins are independent and they can be multiplied by this direct product method. So therefore I get a 4 by 4 matrix, and my operators Ix, Iy, Iz, they will also be 4 by 4 matrices, and this is the way we calculate the matrix representations of the rater of the operator for RF pulses. So here similarly we calculate for Ry pi by 2, I have here 1 minus 1 1 1, this is for spin k. So if I call it for spin k and this one is for spin L, and I take the direct product. So if I take the direct product, I get here 1 minus 1 1 1, that is the same, and then this is basically multiplying with minus 1 this whole thing. So I get here minus 1 1 minus 1 minus 1 here, and this will be 1 minus 1 1 1, and this will be 1 minus 1 1 1, because all these are 1s here, right. So therefore these will be the same except this term will be different. So this Ry pi by 2 now consists of all real numbers, okay, whereas the Rx contain all imaginary i's also. Using such matrix representations for the pulses and the density operator, the evolution of the density operator through a multipulse experiment can be calculated. So put this all in summary, I have for one spin, I have here 1 by root 2, 1 minus I 1, Ry pi by 2, 1 by root 2, 1 minus 1 1 1, Rx pi is 0 minus I 0, this is for 1, and Ry pi is 0 minus 1 1 0. And similarly for the 2 spins you have 4 by 4 matrices, and you have calculated here Rx pi and Ry pi, which will contain only anti-diagonal elements. Notice here, of course here also they contain anti-diagonal element, this is the diagonal and this is the anti-diagonal. So I have only anti-diagonal elements here, and here also I have only the anti-diagonal elements Rx pi, and this indicates this shows how the calculations have to be performed. Okay. So for now we are ready to calculate any kind of a matrix representation, any kind of evolution of a multiple pulse experiment. So if I have a multiple pulse experiment, so I start with the initial density operator rho 0. Start with this, apply a pulse P1 here, and then allow the spin system to evolve under the influence of the Hamiltonian H1 for the period tau 1, then apply a pulse P2, then apply and then allow the system to evolve under the influence of the Hamiltonian H2 for a period tau 2, and continue like this. Therefore, any number of pulses what we might have here, I can continue to calculate the evolution of the density operator through the pulse sequence, and finally I will get the density operator here, which is what I actually measure, and then that contains the entire information about the evolution of the spin system through the pulse sequence. Okay, how do we actually do it? So therefore we say start with the rho 0, this is my initial density operator. So if I put the density operator here, the first thing that is coming here is the P1, that is the pulse. Therefore when I have the pulse, I have the P1 and P1 minus 1, right. So this is the what I get after the first pulse. That means for this part of the evolution, the density operator here becomes the row of 0, this is the new row of 0. So for the beginning of this one, this becomes my row 0. So therefore this is my row 0 for the next operation, and that is the evolution under the Hamiltonian H1 for the period tau 1. So e to the minus I by h cross H1 tau 1, and on this side you have e to the I by h cross H1 tau 1. So now where I am, I have reached here at the end of this. Now apply the pulse again. So if I apply the pulse, therefore once again I multiply by P2 here and P2 minus 1 here. Now if then I reach here, then of course I will have to multiply by e to the minus I by h cross H2 tau 2, and on this side e to the I by h cross H2 tau 2, and so on. So this is the way one can actually calculate the matrix representations of the density operators and evolutions of the density operator through the multipulse experiment, and that is the way one has to calculate it, and I think we can take it forward in the next classes and with the explicit calculation, and see what is the physics and what is the science that comes out of these calculations. So we will stop here.